Now we move on to the second topic of my lectures. This is random walk and electrical networks. Random walks is one of the oldest topics in probability. It talks about a man who's, let's say, starting at the origin and walking on the integer line. The man can take a step to the right or a step to the left, a step to the right with probability half, or a step to the left with probability half. In other words, the man tosses a coin, and if it's heads, he takes a step to the right, and if it's tails, he takes a step to the left, and goes on and does this continuously. And this is the most classical example of a so-called stochastic process, and it has been studied for more than a century. It was originally George Poulier wrote one of the most startling articles in 1928, and we'll discuss that. And the random walk is at the basis of many things in probability. For example, Brownian motion, which describes the movement of an oxygen molecule in space, is nothing but a so-called, in some ways, a limit of a random walk process. What we do today is to understand the result of Poulier through electrical networks. So let me start. So let's talk about resistance. So we know that, so my cursor will denote what I'm talking about. We know that if I have two resistances R of R1 ohms and R2 ohms respectively connected to a battery, and this is the earth, then the effective resistance, if it's connected in series, the effective resistance is R1 plus R2, whereas if it's connected in parallel, the effective resistance is the reciprocal of 1 over R1 plus 1 over R2. So that's the effective resistance. So let's now do a one-dimensional thing. Suppose you have a string of resistance, each of R ohms from 0 to n. So there are n of these resistors connected to a battery. Then the effective resistance is n times R. In other words, rho n goes to infinity as n goes to infinity. In 2 dimensions, what happens? So we have n cross, let's say 2n cross n. So this is the origin, and this is minus n, n, minus n, n. So a 2n cross n, 2n cross 2n square, and at each edge we place a resistance of R ohms, and we connect the battery to the center, to the origin of the square, and outside we hardwire. In other words, there's a wire with 0 resistance connecting the outside boundary of this box to n cross 2n. So the question now is, what is the effective resistance of this circuit? But we will show that the effective resistance, again, rho n of this 2-dimensional circuit also satisfies that rho n goes to infinity as n goes to infinity. In fact, what we will do is we'll modify the circuit by replacing resistors with hard wires, in other words, 0 ohm resistors, so as to obtain a circuit whose effective resistance rho prime n satisfies that rho prime n is smaller than rho n, because after all, we've removed some of the resistors and replaced them with hard wires. And we will show that rho prime n goes to infinity. And if rho prime n goes to infinity, then rho n must also go to infinity, because rho prime n is smaller than or equal to rho n. The way we modify it is that we keep, so this is the origin, this is the box minus 1, 1, minus 1, cross minus 1, 1. We replace the boundary of this box by hard wires. Earlier, if you remember, these were all resistors. of R ohms, but now we have replaced them by 0 ohm resistor. So the effective resistance of this modified circuit is clearly less than or equal to rho n, and let's call it rho prime n. So we do this not only for the box -1, 1, we also do it for -2. 2 box, the outside boundary is replaced by hard wire, similarly everywhere, as you can see. Outside, of course, in the originally the outside completely -2 and that outside was hardwired, but now we hardwire the inside smaller squares also. So the resistors are only the ones connecting an inside box of minus I cross minus I to minus I plus 1 minus I plus 1 cross minus I plus 1 plus I. In other words, an inner box to the box just containing it. Okay. What we can see is that the circuit is equivalent to a circuit like this. Let's see what I mean by this. Look at the first point. The first point here has 4 circuits connected to a hard wire, and that's exactly what I show here. There are 4 circuits, 4 resistors, each of them represented by this red line, connected to the first hard wire. So this is the 4 resistors connected to the first hard wire. And then there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 resistors connected to the next hard wire, etc. The next will be 20, etc. And the last would be 8n minus 4. So what we have is a necklace of resistors with the necklace, the number of wires going from the first pearl to the next pearl is 4 here, and then 12 here, and then 20 up to 8n minus 4. And now we have to find the effective resistance of this. The effective resistance rho prime n is clearly, well, this is there are 4 of them, and therefore it is 1 over r plus 1 over r plus 1 over r plus 1 over r. In other words, 4 over r inverse of that, because these are in parallel. So that is that's r over 4. Similarly, the next string gives us r over 12, etc. The final one gives r over 8n minus 4. In other words, we have r over 4 multiplied by 1 plus 1/3 plus 1/5, etc. 1 over 2n minus 1. And this sum goes to infinity as n goes to infinity. Therefore, rho prime n goes to infinity as n goes to infinity. And since the effective resistance of this modified circuit goes to infinity as n goes to infinity, the effective resistance of the original circuit also goes to infinity as n goes to infinity. Thus, in a 2-dimensional grid, the effective resistance also goes to infinity, just like in the 1-dimensional when we had just a string of n resistors connected in series, and that also went to infinity. This also goes to infinity. What about 3 dimensions? For the 3-dimensional grid of resistors, we will show that the effective resistance rho n converges to a finite quantity as the grid size goes to infinity. As in the 2-dimensional case, what we will do is we'll construct a modified circuit such that the effective resistance rho prime n of the modified circuit is larger than that of the 3-dimensional grid of resistors, and we'll show that the larger rho prime n, the limit of that is finite, and hence in the original grid, 3-dimensional grid of resistors, the effective resistance should be finite. We'll illustrate the modified lattice in a 2-dimensional setup because, of course, we cannot draw the 3-dimensional structure. However, since we know that in the 2-dimensional case, the effective resistance goes to infinity, so the effective resistance of the modified circuit being larger than the effective resistance of the original 2-dimensional grid will also go to infinity from our earlier work. So now understand what is happening. So we have a cube, minus n cubed. And each edge there, except for the one on the boundary, is a resistor of R ohms, each edge. Okay. So we are not modifying it at all right now. This is the original question. So we have a cube now of connected resistors. The origin and the outside boundary are connected to a battery. And that's why we can calculate the effective resistance of this circuit. Okay. In the modified circuit, we remove resistors. In other words, we replace them by infinite ohm resistors, because if we remove a resistor, there's no connection between these two vertices. And therefore, we make it the effective resistance more than the original effective resistance. We also move connections. So, if there were two resistors being connected here, we remove them so that this gets connected to somewhere else and this gets connected somewhere else. So the connections get lost. So in other words, we make parallel connections into series connections, thereby increasing the effective resistance. To do this, we look at the lines x plus y equal to 2 to the n minus 1 and adopt the procedure as given in the picture in the next page. So this, as I told you, I'll just do this for the two-dimensional lattice, explain the modification, and then we'll talk about it, what to do in the three-dimensional case. So the purple lines, so this is the line x plus y equal to 1. This is the line x plus y equal to 3, which is 2 to the 2 square minus 1. This is the line x plus y equal to 2 cube minus 1, etc. So these are the lines x plus y equal to 2n minus 1. Each red edge here is a resistor and the string of resistors starting from, okay, so this is, these are all resistors. And now we will start the resistors from each of the vertex on the line x plus y equal to 2 to the power 0 minus 1. In other words, 0. So these are the two lines where I put in the resistors. Next, what I'll do is I'll look at 2 to the power 1 minus 1, which is x plus y equal to 1. So we'll start resistors from the point xy equal to this x equal to 1, y equal to 0, and we won't connect it here. So there's a we don't connect these resistors to this point, but we put these two in series, and there's no parallel connection here. And then we continue like this, and we continue like this. So I'm just so these are all these red edges. Each of these red edges is a resistor of R ohms. And then after 2 to the 1 minus 1, we go to 2 to the 2 minus 1. So 2 to the 2 minus 1 is exactly this. So there's this point here, and we go like this. And so this is a string of resistors. And there'll also be another string of resistors, which I'm showing in the next page, which is from this vertex, because this is on the line x plus y equal to 3. From here, we go on like this. Then from here, we go on like this. And then from here, we go on like this. Because there's already these exist. So these are the now new resistors which I have added. And then similarly, I do it for x plus y equal to 2 cubed minus 1. So I've just shown them, shown all these here. And next, from the next line, etc. So this is the collection of resistors. So what have I done here? So there is no resistor in between these two vertices. In other words, the original R resistor which was there in the original circuit, I've removed. So I've added an infinite ohm. So in other words, and also there were these connections, which was here, for example, all these where I am bifurcating the connection. I'm not connecting it. So those are, which were earlier parallel, are now becoming series. So the effective resistance of this circuit is clearly more than if it was just the box with R ohms connections between two adjacent vertices. Having done that, let us try and get an equivalent, just like when we had the string of a necklace of resistors, let us try and see whether we can reduce it to an equivalent circuit. Okay. In the first case, I started the infinite length of resistors on the X and the Y axis. So that, let me call it here. Once I go to the first resistor, there's another infinite length going from here to here. So another infinite length going starting from here, and this one, the one on top, I can think of this guy, and the one here. Similarly, coming here, I get 2, because from here I go to the first one that's expressed by this resistor, and then there is a string going along the x-axis that is expressed by this line, and another string going along the y-axis, so the parallel to the y-axis, and that's expressed by this string of resistors. But okay, we actually do not go all the way, because from here we go 1, 2, and then again another string would come, which is from the line x plus y equal to 3. Therefore, what we get here is after 2, we get another set of lines coming out, because when we come here, so this, let us follow this in the x-axis here. From here, there is a one resistor to the first point that's given by this resistor. Then from here, there is another 2 thing, and then coming up to here, then that's given by these 2. And from here, we go up and another one going up, and so that is represented by these 2. Also, from here, we go to the first, and then we go up this way. So from here, this is the first, and then we go up 2 of them, and then again, we meet another string of resistors, and these are given by these 2 lines. Okay. So what are we doing? We have again constructed a necklace of resistors, and we are hardwiring, assuming there's a hardwire on the line. That's exactly what we have done. What we have is in the first line, there are 2, and we are just hardwiring these, this point and this point. Okay, just as you can see here. So, so the first, there are 2, then there are 4, then there are 8, then there are 2 to the n. When the line is x plus y equal to 2 to the n minus 1, etc. So that's what I'm saying. So each k by L, so this is a k by L, 4 by 2 necklace has k strings with L resistors. Okay. So L resistors in each string. So this string has 2 resistors, this string has 4 resistors, but there are 8 of these the chains, and here there are 2 to the n resistors on this line, and there are 2 to the n minus 1 chains. So the effective resistance, just like earlier, doing the parallel calculations, so calculations for resistors located parallelly, we get that the rho prime n is r over 2 plus 2r over 4 plus 4r over 8, etc. So which is r over 2, if you take in common, then it becomes 1 plus half plus etc. And so that sums up to be nr by 2, which goes to infinity as n goes to infinity. And this is not surprising, because we are actually working in 2 dimensions. In 2 dimensions, we saw that in the original grid, the resistance goes to infinity, and this rho prime n is bigger than the effective resistance of the original grid, so this should also go to infinity. But in the three-dimensional case, which I won't draw, what we'll have is exactly another such necklace of resistors. But now what we'll have is between the first two, so we'll have to look at the line x plus y plus z equal to 2 to the n minus 1. In the first setup, so think of it as the three-dimensional setup. So this is the origin. There's one line going along the x-axis, one going along the y-axis, another going along the z-axis. And each of them are 1 ohm resistors, so that connects here. And when n equal to 1, that is x plus y plus z equal to 1, from there we get another set of resistors, another whole lot of chains of resistors, and that is the next one. And here what will happen is that there will be 2 resistors along each chain, and there will be 9 such chains or 9 such strings. So, and then in the next case, there will be 4 resistors along every string, and there will be 27 such strings, etc. In general, there will be 3 to the power n many strings, and in each of these strings, there will be 2 to the power n minus 1 many resistors. So now because these are in parallel, now we can add them up, because the first part, just this part would be R by 3, and then there are 2 each and 9 such strings, so it will be 2R by n, etc., 2 to the n minus 1, R by 3n. That is the last one. And now if we add it, R over 3 over 1 plus 2/3 plus dot 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 2 to the n minus 1 over 3n minus 1. This is a geometric series, so we can sum it up. So it becomes R by 3 times this quantity, which converges to R as n goes to infinity. So in other words, the modified circuit in the three-dimensional case, what we see is that the modified circuit converges to a finite limit, which is R, and therefore the original circuit should be converging to something which is less than or equal to R, because the modified circuit has effective resistance more than the original circuit. And next we will start talking in the next lecture, which will be followed by this. I'll be talking about random walk, and I'll connect it with the electrical network. Okay, thank you now.